Thank you, ma'am, for introducing. Um, so I'll now jump to the main topic. Today's talk is about like the work we have performed recently. That work is actually to decoding a sudden cosmic X-ray outburst, and the specialty of this work is that we have utilized Indian facilities, optical telescope facilities, to understand how this event actually happened and what is the relation with the other other wavelengths during this outflare. So this is the outline of my talk today. So first we'll explain we will go step by step. We'll explain the first what is the spectra looks like, because maybe I think lots of people don't know about this kind of that what is spectra, what is the emission line star. So I'll go step by step. So and now I'll start the presentation. So before jumping to the spectrotechnical parts, first we need to understand that what stars. I mean, what's the essence that we get from looking at the night sky? You can see this there in the night sky we can see lots of stars, and that actually fascinates a lot of us. And if you try to see them a bit carefully, you can see multiple colors they have. Like they don't looks like same all the time. They have multiple colors for them. Also, apart from there, there is another feature some stars show like this. They twinkle, but this is not happening due to the atmosphere. This image was taken by a satellite, and still the stars are twinkling. But why the stars are twinkling? Because it's happening due to them. The stars. It's something happening in on their side, not our side. And this twinkling is a very major property of a stellar system. Now, if we consider like these two, I mean, these two are not like the everything here. There are lots of things happen in the stellar astrophysics part. So we just consider these two things. We have seen this night sky. So what we should do after looking at them, just to get fascinated? No, we should also try to understand or think about looking at those stars. By the way, sorry, I just got this image about thinking. So I just added it here. So now let's go step by step. So first step is that what is a spectra is? The spectra is something like a prism. You throw the light from a source through the prism, you will see this kind of like a continuous spectra. Okay, why it's happening? That some light from a source is coming, and through the prism, when that light goes through the prism, because of the diffraction, it will show all the parts, all the subparts of the lights that was inside the source. Okay. Now, similarly, there is a multiple event happens. So, like if you suppose you are considering a hot, low density cloud of gas, from there, if light is coming, that if you pass through that light through a prism, you will see this kind of emission line, like a black background, and in that black background, you will see separate lights. Now, if we combine this both, the absorption line spectrum, you can see there's like this hot dense energy source like this. This is a, you can think of like a light bulb or a star. The light is coming from that star, and there is this cooler low density cloud of gas. And when the light passes through it, and you put a prism in front of the sensor, you will see the continuous spectrum like the previous case, but with some black lines in it. What's happening is that this cold gas is actually absorbing some of the energy from the source, which is coming from this point, like from the light bulb or the star. So when this passes through it, you will see that these black lines are forming, and that is actually absorption. Now, how this absorption and emission lines actually forms? If you consider like two atomic systems, and if you put some energy, the electron will absorb that energy and will jump up to another orbit. Okay, so what is happening here is that that electron actually absorbs some energy from a source that in this case it was the star or that light bulb. So what is happening that when you're seeing that light bulb and you took it through the spectra, this wavelength, that whatever wavelength energy hits that electron and electron absorbed it, you'll see a black line at that energy. That's how the absorption line forms. Vice versa, when that excited electron goes down from one orbit to another, it will radiate that energy, it radiates that energy, and that energy will show us this emission line, which we saw in this case, like this emission lines form. Now, if we consider this, all this phenomenon, now considering with the like actual star system or a black body system. Now, what is a black body? Black body is actually a source of heat, like a source of all the wavelengths. So, if you heat up an object, that object temporarily can behave like a black body. Means that that object can radiate energy in all available wavelengths. Now, this is a black body which is comparable to our sun. Now, what is happening? You can see it is radiating energy in all these wavelengths, but the intensity, like at the intensity that at which this majority of its energy coming through is a bit different. It's not like a straight line or something. Energy is allocating somewhere here in the visible light range. So, and that's why our sun is having a that's how we have said like our sun is having a temperature of around 6,000. And this is the point. This is a very important point, that why this spectral study is very important. Now, now what happens? Now think about like what happens if we change the setup a bit differently. Now, as we consider, this cloud was having a cold and low density, but now I change that cloud with a hot and comparatively it's a higher density cloud. So now, if we pass through this light from a prism, using a prism, what we will see? We'll see a spectrum like this. Now you can see in the background that similar continuous spectrum is there. This all colors, colorful colors are there. But instead of these black lines, which was forming due to this cold gas, but now it is forming brighter lines. And that is actually the emission in the spectrum. But we cannot use that color image for our science work. We have to put it in an analytical way. Because I mean, may I see a color like green, but that green can be like with different green for other people. So we need to change it into some constant parameter that will not change person to person. So that's why we have used this kind of intensity versus wavelength. Each wavelength represents different colors, and with respect to that, what is the intensity that we are getting from the star itself, and that's how we see the star. Now you can see there is some lines is going up. That means in this color ranges, in this color range, we can see there is a bright line here, and which is like a H beta. So in the H beta, we can see a emission line. So there is a like a hot cloud gas which is actually producing this H beta line. Now vice versa, this H alpha is also there, but it's quite intensive. So that's why like we have like shown only this much here. Similarly, in other wavelengths, in calcium passion lines, we can also see. So before going to the next slide, I just want to give you an like an idea like how a grating like this prism thing actually works. Okay, so just a second. So I brought my green laser here. So this is quite bright. That's why I am not using it for pointing. But if we see this green laser, we can see it's a tiny dot here. Now in this case, I want you to imagine this laser is a star, and this screen is the Earth, or someone who is observing the star, this laser from Earth. Now what he will see like this dot, but using this dot, he cannot like what to say. He can like measure the brightness of the dot. But what else? Like what kind of material, what kind of object, like how this laser actually producing this green light. So what they use this kind of prism. But instead of prism, people also use a grating. The grating will have a very small prism kind of feature inside it, and then they pass through the light through it. And as it goes through that light, it will deviate the light. Now I only have this laser, green laser, so you will only see the green part, green light here. You can see the lights deviated. Now the central part is this main light that is coming through the straight. Okay, but you can see on the left and right there is multiple dots, and each of dots are having almost similar distances. And that distance is actually representing the property of this green laser. If I use, suppose if I use a red laser here, you will see the same kind of pattern here, but the distances between two dots will be different, and that difference will actually presenting this continuum. So that's why red is coming here, green is here, blue is here. You will never get that green and red are having kind of similar kind of wavelength. They will be always different. They are allocated naturally. They are allocated with different wavelength values. Just a second. Okay. So we have understood how this emission line are actually forming and how they actually looks like. Now, if we think about that, there are like multiple types of, depending on the situation in the sky, like what is the situation they are belonging in, like what is their companion, if there is a companion with them, or if there is like a cocoon of dust or gas, something like that. Based on this property, is their mass, all this property, based on this property, we can classify emission lines in multiple categories. One is like this pre-main sequence stars, like these are like newly born stars. The hydrogen fusion may have started, but they are still inside that primordial cocoon of dust. Now there is this early type stars. They are like big high mass category of stars, but they produce this kind of emission line. Then this late type stars are there. They are like almost like lower mass candidates, and they also produce this emission line. And other than that, this closed binaries. This closed binaries means like there's some interaction is happening between two objects, or maybe it could be like a triple object or something like that. And because of that interaction, some interaction happening, we can see the emission line in the spectrum. Okay. By the way, you can see I have marked this BE in yellow. That is because our work is concentrating majorly in this early type stars, which is a BE here. But we'll see like how this thing got evolved. So what is a BE star? B star is a massive B type main sequence star. I mean, B star, there is like a mnemonics where we classify the stars into different category based on their mass and temperature, which is like OBAF, GKM. This is the classification. And based on that classification, B, which is like a massive star. And now we can see like the spectra, this star spectra shows a emission line where this H alpha, as I saw in the previous spectra, this H alpha is the strongest one. Other than that, the mass is it? I think it's visible. So in the mass of the stars are like around 3.6 to 20 solar mass. So like they're like quite massive. They can have up to like 20 solar mass, like 20 times heavier than our sun. Then also they can have a radius of 11 solar radius. I mean, you can understand like 15 times bigger. They rotate very fast. Very fast means like they're very close to their critical velocity. When critical velocity means like if it goes to that critical or go above that critical, the mass from the surface, the material from the star will come outside from the star. And now this is one of the major property of B star. Is it surrounded by geometrically thin gaseous Keplerian disk. Because of this rotation, the stars actually ejecting matter in the vicinity of its own, and because of that, it can form a disk around it. This is like a well defined now in classical B star. Also, there is other possibility that how this disk actually formed is something like due to pulsation. Means that star is more like a breathing. The diameter is like increasing and decreasing, and because of that, the mass ejects into the orbit. So this is another, but still research is going on. Like, what is the best combination? Like, how these two phenomena is actually contributing for generating this kind of gaseous disk. Now, this is the like HH diagram. In HH diagram, we can see this is our sun, like where the sun belongs, and this is the high mass region in the HH diagram. They're really big stars. Okay, so what is like then we have understood like this is a B star. Okay, fine. So what tools we need? We need another tool, that is this X-ray astronomy, X-ray in astronomy. So what is X-ray? Human body generally radiates at around 100,000 angstrom. So if you have a camera which can detect this wavelength, you can see a human glowing, I mean, literally glowing. Now, if we compare this sunlight and bulb, they are approximately having 5,000 angstrom. So you can see it's visible. You can see it by, I mean, from your eye, using your eyes. So, and the color is generally is yellow. Now the hot star surface, like this high mass stars, they are having general peak. Their surface temperature is having like around 40,000 Kelvin, which is falls around 750 angstrom. So they are pretty hot, and their majority of their energy comes out at this is actually the ultraviolet range. Now there is another part. This last one, the really hot plasma. They are having like around 50 lakh Kelvin temperature. They're really hot, but their signature, we can see the majority of the energy comes at 6 angstrom. This is very low. As the angstrom goes lower, the energy increases. So this is the X-ray, and why it's important to study such a low angstrom values or high temperature. Let's see our sun in X-ray. If we see, you saw multiple imaging Google, like the sun looks really beautiful in multiple colors or something like that. But if this is the X-ray image, and if you see carefully, you can see there is some black. This is not bright. In X-ray, actually, sun is not very bright. But when you put it like that, you can see other materials around the sun, like this kind of something is coming out of the sun. This is actually the very hot plasma around the sun. This image has been taken by the soft X-ray telescope S60, which is on board the orbiting Ezhikode telescope, which is a Japanese telescope. Now this hot plasma, I mean, by observing this X-ray, you can see a beautiful image. That is fine. But what we can study? We can study the property, what is happening on the surface of the sun. If we see carefully, then we can see these strings or these filaments here. And we can understand that there is multiple, we can map like a magnetic field, magnetic orientation, magnetic changes on the surface of the sun by studying this plasma. And plasma is a charged, plasma is like a charged electron with a very high temperature. And if we consider that thing, they will follow the magnetic field. And by studying plasma, we can map this magnetic field on the surface of the sun. So studying X-ray is really important. So this is our sun, typical sun. And if we compare it with like a normal B-type star, we'll get like kind of this, like they're really big. Here I am showing this the property of HD 45786. This is the star on which we have done our recent work. This star is having like around 20,000 Kelvin temperature and having a mass of around 10 to 12 solar mass and having a radius of 11.8. Now, why we are going to study like X-ray? For sun, it looks really nice, but what else we can get from studying in the like far away objects? Because though they are big star, but they are very far away, so they will be a dot in the sky. By observing, you can see this is the Orion Nebula. This is the star forming region, and if you see the same part in the X-ray, you can see it's a totally different image. So this is the Odyssey, a 45,000 Kelvin O-type star. You can see that star is really brighting, like it's really bright in this range, but which is not like properly visible in the optical. So this is a like an intrinsic, you can understand like this is a O-type star or not. That is now we can clearly understand by observing the X-ray data. Now, is it only there? Like this is fine because in the sun case we saw this kind of plasma and this kind of feature, magnetic field, all those stuff. So can we see all those things for these stars? No, we cannot see that because they will literally a dot. I mean, we cannot see the features. But if this plasma is changing on the sun, so that will also change its also changes its X-ray properties. So someone is staying very far away, they can see that changes, slight changes in the sun surface by observing the X-ray. Because when this plasma got to change its direction or something, the intensity of X-ray will also change. So because of that, we also change our tactics to study X-ray. And that tactics is to study light curves. We cannot take just one snapshot of X-ray and we can put out some result like something happened. No, we cannot say that. For that, we need some continuous observation, like what kind of change is happening on the surface of that particular star or in the vicinity, because we don't know like where the, I mean, how the exact situation, what the exact situation happening around the star. So all we can understand that changes, when it's showing some changes, we can understand based on that changes. So this is a like a, this blue region is zoomed in here. So you can see like in this particular star, this observation happened using this integral satellite, which is another X-ray satellite. So you can see there is a like periodic brightening up. This X-ray is like continuously giving bright pulses in this X-ray. So by studying this, we can understand the period. If there is like a binary star is there, they're rotating, and because of that rotation, if they're like showing this kind of feature, or maybe something happening around its vicinity, if there is like a dusty disk or disk or a gaseous disk, and something is happening on that. So we need this kind of continuous long observation to understand exactly what is happening in those dots. So let's prepare our next tool, that is the binary stars. In case of binary stars, they are majorly classified based on how people had detected them. So if we see, there are like visual binary, spectroscopic, astrometric, and eclipsing. Now visual binary, as you can see, like you can see them that it's a visual binary, two stars falling one side by side. But the thing is that this thing needs other verification also. Like I'll come to that point a bit later. So this needs other verification, but you can say like they're visual binary at some point. Now the spectroscopic binaries. Now all the telescope or your eyes, I mean, cannot resolve everything. Like if your eyes can resolve your mobile screen, then you will see always you will see pixelated image. But it's lucky that your eyes cannot resolve very small details. That's why you will see a smooth image in your mobile screen, because there are lots of pixels are there, but your eye cannot detect each pixel separately. That's why you can see a smooth image. But that same thing is actually problematic here, that if we cannot able to resolve that, we cannot see the binary star. But there is another tool, this spectroscopy. In the previous slides, I showed you that there is this dark lines, these absorption lines are there. But if there are binary stars are there, they will like rotate around each other. And because of that, those black lines will shift left and right. And by based on that shift, we can study that if there is another binary or not, that how much it shifted, like blue shift and red shift, and how much they shifted. Based on that, we can measure the mass of the candidates, like how fast they are rotating, what's the orbit, something like that. Now it's astrometric binaries. They are like also similar. We cannot see them. Also, it's very hard to detect this astrometric binary using spectroscopy, because the majority reason can be like the one object is very bright. You can see that in optical or maybe in other wavelengths, but the other part is not visible at all. It's very tiny. It's comparatively very tiny with respect to the major candidate in that binary system. So in that scenario, we use astrometry. Astrometric binary, it will be something like that. Will track the star, that how that star is moving in the sky. Like it will shift slowly in the universe. So in the sky, it will move. But if the movement is straight line, then the star is not obstruct. Like the star is like going without any problem. So there's a high probability it's not a binary. But if the star is moving in a wobbly manner, like it's going not straight, but it's bit going down, then going up, something like that, like a sine wave, then that means there is something that is actually stopping it going in straight line. So the center of mass of that system is not exactly inside the star; it's outside. And by that wobbliness, we can understand that if it is an astrometric binary or not. And the eclipsing binary. Eclipsing binary means like two stars are rotating. By studying their light curves, we can understand like how like two stars are rotating. Like if the star is like in front of you, like two stars are in the line of your sight, then you will see you will see like a less light coming from the system. But when they're side by side, you will see like more light is coming from the system. By understanding that, you can study the eclipsing binary. Now, all of those things is like we can detect a binary star. That is really good. That is really nice. But there is some problem happens. If some candidates that is literally not satisfying all these four scenarios, like you cannot detect using all these four. Spectroscopic, no. Astrometric, no. Eclipsing, no. because the other candidate is really small, or maybe something else like a compact object. So because based on that, we need some other wavelength to see those stars, not in optical. You cannot do that in optical. And that is where X-ray binaries comes in. In the X-ray binary, we'll wait and try to see like if any X-ray is coming or not. And there is like other feature can happen. But also if something some interaction happen with the candidates, I mean the main star and the secondary star, and if some interaction happens, we can see X-ray for that. I mean that interaction can produce like some other scenarios are also there, but this X-ray binary is one of them. So by this X-ray observation, you can also predict the binary key. So binary star with compact object. In this case, because we already see like this previous four options are not applicable in this case. So definitely the object is more or less like a compact object. They are very small. So compact object is something like a neutron star, white dwarf, or black. In this case, in this study, we have used this neutron star and Hema stars. So you can see there is lots of this, all combination can happen in this case. But our concentration will be only on Hema star with in combination of neutron star. Now, if I just give you an idea like neutron star, how small this can be, what to say, like if we compress the sun into a neutron star, I mean, sun cannot be a neutron star because of this Chandrasekhar limit, that cannot be. But suppose, imagine like it came down to like a neutron star, become a neutron star, then the radius of the sun will be something like from this campus to Rajaji Nagar in Bangalore. So you will be still inside the Bangalore, but there will be a neutron star with you. So this thing can be I mean, you can understand like this is literally very hard to see because one star will having a radius of something like 15 times the sun, and other one is having like in like 10 kilometers or some 12 kilometers radius. So literally that is not visible. That will not produce much of light, at least in optical, invisible. Because this like larger surface area, more light will come. But what about X-ray? This large star, is it capable enough to produce enough X-ray? No. But this one, this small object. Because you can see in this image, this is like a simulated artist image, so don't take it very seriously. But just for a basic idea, the mass is falling from the stars to into this. This is a picture of a black hole, but you can imagine like a neutron star here also. So it's a accreting matter from the donor star or the primary star here. And as it falls inside, you can see the color changes. This is yes. So you can see here, this is the star which is having like a reddish color because it's having like a lower temperature, surface temperature. But this they have depicted it in a bluer color. Means it's radiating something which is having a like a higher temperature. This light is coming from a higher temperature source. Now, what is this temperature is actually? So this temperature is actually forming because of this matter falling into the star. They're exactly not falling into the star. It's something like this neutron star. It's driven by the magnetic field. This this neutron star can have like 10 to the power 8, like in billion order of magnetic field. For a comparison, in Earth right now, I forget the name of that lab. They have created the most the highest amount of magnetic field they can generate was something like around 5 or 8 Tesla, something like that in this range, and that is really dangerous, like 5 and 8 order of Tesla of magnetic field. But in this case, they are having 10 to the power 8 order. So it's really high. Now, when this matter falls, this surface matter from the star falls into that, they are driven by this magnetic field. And when this matter driven by this magnetic field, they generate X-ray because there is a huge gravitational potential difference is happening, and that actually release a lot of energy. So now we're closing to our main work, what we have done. Now our work is based on this BeXRBs binary system, BeXRBs. So what is the major property? As I just said, I'll just repeat again all those. BeXRB, a major subclass of high mass X-ray binary that consists of a B star and a compact object. As I just say, like they are high mass binaries, and they are having a compact companion. Now this compact object rotates around the donor star in elliptical orbit. They're not, I mean, almost like most of the cases, they don't rotate like in a circular manner. Now, this BeXRB can be persistent or transient in nature. If you observe this X-ray pattern from the stars, you will see like they can be like persistent, like there will be like no change. One smooth line, like the X-ray is like not changing much. But sometimes you will see burst, like some high intensity X-ray is coming, and other time it's not. Now, in the system is classified based on the outburst characteristic. This BeXRB also classified based on like type 1 and type 2. When the X-ray luminosity is like around less than equal to 10 to the power 37, they considered as type 1, and this is like more regular, like this kind of outburst happen regularly. But in the other case, it can be like greater than 10 to the power 37, and they are like not so much regular. They can be very frequent, or you can maybe in the history of that star we have seen only one, and that is actually case happened in our work. So how all this work, like what we have done, how this everything is got started. MAXI J0709-159. This is actually the source, which is where this MAXI satellite attached to the International Space Station observed an outburst. That outburst looks like kind of this. Like you can see these circles. This is the field of view of that satellite, and based on that, you can see there is this red patch. Red patch means more X-ray came from this particular location. And if you see after that, just after that, you can see there is that red patch is not there at all. And why is that? Because now that flare is not there. So we'll say this as a flaring event happened. After that, it's now cohesion phase is going on. Like it's now got stable. Now we'll check now in this direction, in this same direction, as I showed into the previous slide, that there is one star, HD 54786. That star is also in that same location where this X-ray came from. Now we have to check, like is there any clue of visual binarity, like if we can see, or that X-ray is coming from like a non compact object binary system. So we tried to check that. We have took the optical image. This is the optical image, SGSS 9. This is actually the red filter. Through that, we can see there is only one star. This black patch, I mean, don't consider it. This is like some reduction error, something like that. And in the 2 months, this is the infrared. Clearly, it looks like a binary. I mean, there is another thing here, like it's like bulging out in this side. So it's a binary. I mean, that's really good. Or is it? We checked it using Gaia EDR3 data. And we found that Gaia EDR3 having totally different value for those two objects. These two objects, Gaia EDR3 showing totally different. And based on that, we said, no, they are not binary. They are not visual binaries. Now, as I said in the before, in the visual binary case, we need other validation or other clarification. And this is how we do it. We try to see like what is the distance of the object, what is the distance of those objects, are they like close to each other, or they have similar astrometric properties. In this case, they are not. So that's why we are saying they are not visual binaries. Now we have so in the next process we have did the color magnitude diagram. In the color magnitude diagram, it's a very important part in this kind of study, because this will inform us about the slope or the energy slope, how like the star is behaving, or where the star is going, the path or life cycle of the star. This information we can get. Now I'll try to give an example. Like in a car race, suppose there are two cars are running. Now what is more important? The speed of the car. I mean, obviously the speed of the car is the important thing here. Now what is more important? The velocity of the car with respect to the road, or the speed of the car with respect to the other car. The other car is more important. So then you can estimate, like, are you going to win or lose? If you're having higher velocity than the other one, then there is a higher possibility that you will win. But if it's a negative value, so the other car is having higher velocity, so you can lose the race. Similarly, in case of scalar system, this color difference is very important. This color difference will tell us about that if the star is evolving, or it's like a pre-main sequence, or it's a giant, it's a supergiant, those kind of things. And that we do using this color magnitude diagram plot. In this plot, we can see this cross is this HD 54786 star, and we can see this is actually following this orange and green intersection of this orange and green patches, and that is the location where we see like classical B stars and the giant star are actually overlapping. So based on this information, this kind of velocity or color difference, we can say that this star is a B star, but not exactly a proper B star. It's evolving. It's not exactly like a young, early type. I mean, the age is low, something like a young star. No, we say it's a B star. Still now, it's a B star, but it's it's aged now. Now, this is another parameter we use to study stars, which is the spectral energy distribution. In this case, we have obtained all the available magnitudes of this HD 54786 star. And by compiling all those data with respect to a model star, this model star is like calculated. This is like we made this star in our lab. And based on the material, what material can reside in a star surface, stellar surface, we plot this absorption line as we showed previously, like the absorption line can, how it forms. And based on that, we plot our actual data from the star with it. And as we see, this is a proper fit. And where it fits, when we compare it with a model of surface temperature of 20,000 Kelvin, and the surface gravity of around 3, and the radius of around 11.8 times larger than the sun. And this point, we can see that all this data are matching properly. So this is how we also got some intrinsic property. We got to know some intrinsic property about the star. Okay, so we have got stage ready, like what information we have found about this particular star HD 54786. Now we will concentrate on, now we have concentrated on the part like how this interaction or this kind of change, this X-ray, how that thing, this changes happen. Now we use the spectra using Indian telescope facilities, which is the VBT. It's a 2.34 meter OMR, low resolution optical telescope. Again, and also HCT, which is resides in Leh, Ladakh, which is like a 2-meter telescope, and this also have a low resolution optical optical system, and they are using like something like called OMR instrument and HFOS system. These two instruments are actually attached behind the telescope to take the spectra from the telescope. And we took that opportunity to take 4 consecutive spectra on February 1 and February 2 using this both facilities. Now, why it was very important? That why we took immediate spectra. We can wait for some months and we can like wait for the when a proper time will come and then we'll try to see what happening in that stellar system. But no, we took immediate because this flare happened. And because that flare happened, we took immediate spectra, and that spectra looks like something like that. As I show you, we cannot show you this colorful image anymore because that is useless. So we converted them into a proper spectral line. So I'll come to this point late a bit in the next slide. Now, from that spectra, what we saw, majorly what we saw, we targeted the emission line, those lines that is going above this continuum, like this spectral continuum line. In this case, we have seen like H alpha is there. And also, as we have taken spectra 2 days, like 1 and 2 February, we saw there is a change in the H alpha. So it's reducing, like it got down from about like 0.7 angstrom. So the intensity goes down. Also, we saw helium line, helium 1, O1, and Passion series line. Passion series is something like hydrogen, lower energy transition. So in this is like a few of the results we are showing here now. But the main thing is that we saw helium 1 again. And that is a very critical part here. Now, if we see carefully, this 2 has been taken, this one is taken from HCT, this one taken from VBT. In this case, we can see this helium and this heliums are there in emission. It's properly going upwards. Now, this is the data is taken from this amateur data set like BESS, where we again see this helium was there. But this data was taken on like 2012. But on 2018 and 2020, we can see this helium is not there at all. This helium, this upward lines are not there. So something that helium, suddenly this helium presence is gone. Again in 2022, it's reappeared. Now what happened? So something is happening during this time period. Now helium formation is very critical because majority of the material in the disk is the hydrogen. Now formation of helium that needs a very high temperature. So this kind of temperature like cannot be formed just normally. It needs some external force or maybe some kind of critical thing happen on the surface of that particular star. Now something. So in this case, people can estimate like binary interaction. So something crashed in, and some difference happened in the disk, and because the difference, there high temperature, high zones are created which are having very high temperature. And that is the reason this helium is reappearing in the spectra. So that's a very nice clue that we found from this optical part. Now let's see the X-ray part. Now in the X-ray part, we can see during that same time, within that 1 or 2 weeks time, we can see that MAXI, I mean, at that time, the raw data was not available. This processed GSC data was available. GSC is the name of the camera that MAXI is using. And that in that perspective, it saw like a luminosity of 10 to the power 37. And in the definition, it's more like a type 2 outburst. So something happened in the type 2 outburst. So indeed, something happened, and that footprint is also continued in the optical part. That's why we also started seeing helium. So it was not a very small thing. There's some big interaction happened. And after that, Newstar also observed that, but it was like around January 29th, it's something like 4 days later. Now it's came down to 10 to the power 32. It's now quotient, like not much activity is going on. So now we can say the disk is more or less like stable now. So in this time, something happened in the disk, but this time it's again becomes stable. Now this transition will take time. This node don't go like suddenly 10 to the power 37. Just after that second, it will become 32. No, it will take time slowly. Maybe right now, if we took another sample, it maybe goes down like 2 degrees more, like 10 to the power 30, maybe now. So this is the X-ray data that we have analyzed. And based on that, we can see this is the Newstar data. This black line is representing the background. Like if there is no activities going on, then the dots, then the data points should allocate around this line, and which is happening here. So this is the quiescent phase data that there is no activity anymore is there. And this is based on 29th January. So the conclusion and future, that what we have found and what we have seen and in which direction it's actually going, what we have predicted out of all, combining all these data like BeXRBs, spectra, optical, X-ray, all those things. We can see here that in that case, we can see this is the H alpha, like the intensity of hydrogen in the disk. We can see it's going up during this time. This is the time around like 2018. Again, 2020, it's going up. Again, in 2022, this is when we took the data. It's again going up. And we can see it's again dropped down. And this is when this flaring happened. So some activity happened and it loses some of its hydrogen. That can be a possible event. And because of this losing, it actually loses its intensity as well. Or maybe it didn't lose it, but it's reallocated in some other mechanism. So those things actually like we are now we are going through properly with proper study also. Now, if we see the light curve, this is a V magnitude light curve. It was also going up. So there could be a possibility of correlation. We are also like trying to fetch more data after this. Like this is 2022 line. So after this 2022, we are fetching more data so that we can understand that how this thing is going on in the future. As we can understand like how this increment is going, based on that we can understand like what kind of event happening around the star. If that the secondary objects is like where that object is around the star, what is the shape of the orbit, how big that orbit is, all those information we can get from this plot. But this plot is this is an incomplete plot here. because we need this information in this other part, like this plot should continue here. And this information we are actually gathering at this moment. And as we get this proper information, we can understand the periodicity of that system. Because we don't, still now we don't know that is a compact object. But we are estimating based on the literature value that it's a neutron star, possibly a neutron star, because this kind of system resides majorly with neutron star. But what happens if it's a black hole or maybe a white dwarf? There's a lesser probability of white dwarf because white dwarf don't generate this much X-ray. But in case of black hole, they can do that. Also, they can generate higher energy. So we are waiting for next outflare. And that is what we propose using this plot. So this is like a estimate. I mean, this is more like a picture. Like this is a simulated image of how this system. So now let's gather all this information. Like we have seen this spectral change. We have seen this optical image. We have seen this neutron star. Sorry, this X-ray flare. And if we combine all those things, this could be a like an estimated image that how the system is working. I think this one. Okay, just a second. So now you can see in this image that there is a star is orbiting another star. So this center, this big star is actually the B star, and it's having a big gaseous disk around it. And this is a particular compact object, and this is a highly elliptical orbit. And as it goes far away, we cannot see anything, any X-ray activity or something disruption in the disk, in the optical. We cannot see it. It just looks like a normal B star. But as this star comes closer and closer, this compact object start interacting with the disk. And as the goes closer to the star, the density of the disk also increases. And as it increases, the effect in the optical and X-ray also increases. And at some point, it may be so much accurate. I mean, obviously, this star, when it goes near to the star, because of its own gravity, it will accrete matter from the disk. And when this accretion happens and the density of the disk is increasing, this accretion process also increases. And as it increases, X-ray to optical, all those things also, all those footprints also we can see in the spectra and in X-ray. And after combining all those information, this is an estimated image. But to understand the size of this orbit, like how far the star will go, and what is the size of the disk, what is the shape, what is exactly radius, how much evolved this star is, we need to understand the period of this candidate, of this neutron star. Like at what frequency that star is coming close to the star, again going far away from the star. And based on that, we can calculate that. So in this case, we have estimated this is a possible neutron star, but based on like we are still collecting this optical spectrum for this candidate using again Indian facilities, and we are going to we are analyzing it to understand the orbit, and we are also waiting for that if there is some next flare happen. So then we can correlate that there is some kind of correlation that what is the orbital size was there or not. So this is the paper. So whatever I said just now, this was like the struggle of like 45 days of struggle. From the first flare point, we got the data that some flare happened, and this is the data, and to send it to the journal. So this is the resultant output of that work. So you can go to the particular site to read that paper. I mean, you can go through the lot. I have like cutting down a lot of things here, but you can go in more detail. And this is the our team. This is like specialization of this is a three groups of specialization in our department is a stellar astrophysics, galaxy study, and astronomical instrumentation. So you can go through them in our CRISE website. Thank you. Is there any question? Hmm? Hmm. Hmm. Yeah. Oh. Oh. Yeah. This one. This one actually that BSS sample. We took it from that amateur data. So this was like around 2012. So when they took that data, they found like the H alpha measurement was quite high at that time. So actually, this is like one part I haven't mentioned here. Why we need the future data here? Because we can see if we consider like 2008, there is another kind of sample was light curve was available, V magnitude, and you can see it was also increasing. But at that time, no spectra was taken, so we don't know the H alpha change. What happened? But after that, in 2012, this high H alpha was there. So we can predict that if we go through, so there could be another flare can be there, can happen. But we cannot say it. We don't have any proof for that. But this thing can be validated at some extent if we see some changes in the future. So that future will not just say about this, like what is actual happening here, but we can also validate the past data as well in this case. So in this case, yeah, I actually X-ray flare. Yes, 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 yes. This one actually like observing a very small telescope. This one. So that's why it's maybe like here, but it can go like bit higher. It was like around like a 10-inch telescope has been. This is a more like amateur data, and the resolution for the spectra was around like 50 R. So it was a very low resolution. So though it was there and justified, so that's why we used it. But we hope that if it was proper data, and by the way, this observation happened after the flare. It happened like around 27th. Flare happened 25th, and this observation happened on 27th. So already flare done. But during the flare, if someone take, it can be like possibility that it will be a bit higher than that. Hmm? Yeah, BS database. This all three were BSS. This one is from like this one also BSS, but this two is from our professional Indian optical facility. And you can see like they are like quite low because this is taken on February 1 and 2, like around like 10 days after, I mean 7 or 8 days after this year. Hmm? Hmm. Yes, exactly. Yes, yes. Yeah, we can say something about it, but if this similar plot was there, because we can see the V magnitude was increasing and also we can have a correlation with the H alpha. Uh, we tried, but with respect to individual light curve, if we consider, we tried to use machine learning in this case, like oversampling the number of magnitudes here based on this observation and based on some well-known light curves, like where they have known, like after analyzing what kind of data they have found out. Based on that, we can feed those information in the machine learning, and they will compare that continuously with this one, and they can predict some other points inside it. And we can correlate this with then again with the H alpha. But the problem is that the frequency here is very less. We need a proper frequency that should be higher than the sample size, and which that was not. So we are not able to satisfying the machine learning requirement there also. So that's why we didn't go with any kind of in-depth analysis. And that is where we are saying like we need future data to validate this one. If we see the similar pattern like this in the future, then we can understand like there's some past flare also happened during around like 2010 to 2013 year. Yes, we have H alpha after this. We have already taken the H alpha, but we are also like constantly tracking like if any V magnitude data is also available or not. Measurement now. right now we have only analyzed one spectra out of it. So the H alpha is coming around like this is happening around like 17 angstrom. So right now it's coming around like 16.9. So they are within the error range. So we have to check the other ones also. So this these are planets or habitable planets. Okay. So there is a good question that if uh, prob Pravir Adhikari, he's asking that do these B star have planets or habitable planets? I mean, these are really giant star, and these star usually have this kind of gaseous. It's really hot, so like it's really hard for a planet to sustain in that situation. So they usually most of the time, I mean, there is a lot of a higher possibility that this system will not have a planetary system. But as I say, in the emission line star case, like there are other stars like this premium sequence, low mass, all those things. In low mass category, there is a possibility, but in this case, it is not. SDSS image, spectra. Oh, 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 oh. Oh. Yeah, yes, no. Why? I'll tell you. Because we are taking spectra, okay? So how much data we are actually trying to get from the observation that we can set. Like we'll put such a, I mean, we can put a plate in after the telescope, the light is coming now. Before the spectra, we can put some plates there that will limit only this much we can see in only within this range. This thing will be masked out. Okay, so that's how we can only we can like observe like a particular star in this case. I mean, this thing will be masked out, so no problem with that. Yes. Uh-huh. Yes. Yes, this is the location for this HD 54786 B type star. Yes. Hmm. Yes. Yeah, that's a good question because like in this case, if you try to see like there is a quite a lot of overlapping. Okay, and one thing, and second thing is that we are only making it like we are saying this is a we have estimated it. We haven't proved it. We have estimated. This is the estimation. And if we say in estimation like this is a definitely this is a B star, that will be wrong because of its estimation. This is like you can see this is the classical B. This orange one is the classical B one. Sorry, B star range. It is coming out at the corner of that, and it's well inside that giant wave. Okay, but this giant star distribution, it is also have its own caveat also. Okay, so there could be some giant star. You will doubt after going through that sample, are they really giant star? So those kind of thing is there. So that's why we are not saying it's a giant or it's a totally B star. We are saying it's a somewhere in between that it's evolving into a giant star. So there will be like both property will be sustained. So, hmm. Instead of black hole, if it's so the first of all, the first thing you will try to see this X-ray flare, like how intense it is. In this case, it's coming around 10 to the power 37. But because of a black hole, their rate of accretion will be higher than that. So the generation of X-ray will be higher in that case. And as I say, like in the BeXRB, we can categorize it type 1 and type 2 based on this 10 to the power 37, and it's coming around 1.67 into 10 to the power 37. So it's very close to that range. But if it was something like a black hole, then it could be like go like 10 to the power 38, something like that. I mean, I'm talking about the lower range here. But if that is the case, I mean, we don't know. Maybe in the next flare, if we see this kind of energetic output in the X-ray, then we may consider this also a black hole. Maybe that the black hole didn't go very close to the star, and because of that, it didn't accrete much of the matter, and that's why it showed a very less X-ray activity. But if it's a neutron star, it actually goes very close to, and it showed this kind of 10 to the power 37 activity also. But if it is same distance, like suppose like if the star, if the neutron star is coming, suppose like what to say, like 3 AU from the star, and a black hole is coming at the same distance, neutron star will give 10 to the power 37, but black hole will give 10 to the power 38 or 9, something like that. But if we take the neutron black hole far away from there, like suppose 10 AU, and then we can see that black hole is actually producing 10 to the power 37. So this kind of variation is there. But in comparison to optical, we see this helium line, and helium line actually usually form close to the star. So that's how we can predict that it's a neutron star, because neutron star can produce, for example, I said you, like this 10 to the power 37 can come from like suppose 3 AU distance, and it's really close to the star, and there only this helium can actually form. So that's how we are actually omitting this black hole possibility for now. So later, if we take more data, if we got more light curve in X-ray, then we can understand like if something else is happening here or not. Yes, pulsation, yes. And that's how this period analysis in this kind of study, period analysis is the most important. I mean, whatever work goes out in this case, majority are hovering around this pulsation, like how this pulsation rate, what is the orbit, what is the pulsation, also the rotation of this neutron star also. So this information is very critical in this. Uh, yes. Uh, yes. Uh, 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 no, this is, I mean, this is really like a very easy way to do that. First, we'll see when the X-ray pulse is coming. Okay, suppose one pulse came today, you saw that, okay, there is one pulse. Now you see like after 2 days, there is another pulse. Now that's this much data you have only. Now you shift to the optical data, and you found a very good, nice sample of Vmax. Like they took every day. They took every day this V magnitude. Now you'll compare this V magnitude changes with respect to this X-ray flare. Okay. Now from that V magnitude, means this optical part, you will get an idea about the disk around us. Okay. And from the X-ray, you will get the idea about the interaction that is happening due to this star. So if you cannot see this kind of any activity, that's when this neutron star is not close to the disk. But as you see that V magnitude increases, also X-ray flare happens. Now you can understand that it's now close to the star. And based on these gaps between this period, you can understand that, okay, so how much time it's actually taking to make the flare and to increase the Vmax, and after that, how much time it's taking that Vmax is going down and the X-ray flare is now in position. So based on this combination, you have to understand like the orbital period, what is that? you.
Like, you're making everyone understand what are the ways. Actually, you're talking about. Thank you.
Thank you.